today I'm talking about my recent work about joint multi-pitch detection and score transcription for polyphony in piano music. As some of you know, that automatic music transcription is a task of transcribing a human or machine-readable musical score from a music recording using computer algorithms. There are different data representations for music scores. It is common to get whether a piano roll format transcription, which is obtained by multi-pitch detection, or a score format transcription, which is score transcription. You can see an example of music recording, piano roll representation, and a score in Western staff notation in the right figure. And in this work,
Lele, maybe you can switch off your video so that because it seems that the connection is not so good. Your video. Yeah.
My video.
Yeah, maybe you can go ahead. Sorry, I
sorry.
For you. Yeah.
Okay.
Yeah. Thanks. Yeah.
Oh, okay. And in this work, I'm doing a joint multi-pitch detection and score transcription in a multitask format. And here is the multitask model. It is with one model input in the audio spectrogram format and 3 outputs, 1 piano roll, 1 right-hand symbolic score, and 1 left-hand symbolic score. And the model is composed of convolutional layers for feature extraction and bi-RNN layers for on top of the CNN stack for piano roll prediction and sequence-to-sequence models in parallel with RNN layers for score transcription prediction. And for piano music, we separate notes for right and left hands as in 2 sequences. And in the left figure, we provide an overview of the model structure and an overview of the sequence-to-sequence model we use. We use an attentional mechanism in the sequence-to-sequence encoder and decoder. Towards the experimental data, we used a synthesized data set with scores collected from musical websites, and audio files are synthesized using 4 piano models using the native instrument contact player and 3 piano models for train validation, and all the 4 piano models for testing. A train validation and test ratio of 8/1/1 is used. And in the right table, we provide some dataset statistics about the total hours, total notes, and some information about the time signatures and key signatures and polyphony levels. We did 2 experiments. The first one is on different input spectrograms. We made a comparison between different types and parameters of audio spectrograms for model inputs, including SDFT, MEL spectrogram, CQT, HCQT, and VQT. And we provide results in the right table, which shows that the latter 3 spectrograms shows better performance, VQT shows the best. And by testing different parameters, we found that higher frequency bins tends to have better performance, and multitask model outperforms single task model. Experiment 2 was on output audio representation. We made a comparison between a Lele representation and a reshaped representation. And for results, we evaluated using word error rates and specific evaluation metric for score transcription called MV2H. Results show that reshaped representation outperforms the original Lele representation in both accuracy and in terms of time and memory resources required. And also, the same as input representation, joint model achieves higher accuracy than single task model. And here, I share some transcription examples. It is example 1. The first line is the ground truth, and second line is the transcription. Let's play it a bit. Hope you can hear the sound. And here is the transcription. And second example, the left speaker is the scores for the ground truth and transcription again. And the transcription. That's it. Thank you. And this presentation is based on our previous paper submitted to presented at ICASP. And for any questions and suggestions, feel free to contact myself through email or others. Thank you.